Welcome to part 4 of the MSP432 MCU training series. In this section, we will cover the clock system and the memory system. Both are unique and new to the MSP432 P4XX family. From a high level, the clock system on MSP432 is highly flexible with a wide array of clock sources and distributions that you can essentially mix and match clock source to be used for which peripheral. The clock systems are divided into two domains, one suitable for high-speed, high-performance operation, while the second one more optimized for the ultra-low power consumption. So these two clock groups can be combined to cover a wide range of operating frequency, starting at just 10 kHz all the way to 48 MHz. There are also many features that are built into the clock system to ensure the robust operations that can be easily reconfigured on the fly, as well as different fail-safe mechanisms that allows you to automatically switch back to internal sources in the event that external sources become unavailable, such as a crystal or oscillator fault. There are 7 total clock sources available on the MSP432 P4XX family. Starting off with the high-frequency clock sources, we have the digitally controlled oscillator, or DCO. That is an internal and most popular clock source that allows you to generate high frequency anywhere from 1 to 48 MHz. You can also use a high-frequency external crystal to source a high-speed frequency clock. Both DCO and the high-frequency crystal can operate up to 48 MHz. Next, the MODOS is an internal oscillator that can operate up to 24 MHz. And the MODOS is really suitable for internal analog operations such as ADC or flash. So the 24 MHz clock source is necessary to run the 1 megasample ADC. For lower frequency operation of the internal peripherals, you can also use the sys-osc. This is an oscillator that runs at 5 MHz. Moving on to the low frequency clock sources. Starting off, we have the low frequency crystal. That is a typical 32 kHz crystal that you can use to run an accurate RTC clock, for example. We also have an internal oscillator called REF-O. This REF-O is an internal oscillator that can generate a 128 kHz clock signal. It can also be divided down to 32 kHz. Lastly, we have a very low frequency oscillator. It is yet another internal oscillator that can generate around 10 kHz clock signal. So altogether we have 7 clock sources, and these 7 clock sources can be used to feed into 5 different clock taps on the MSP432. Starting off with M clock, which is the main clock being used to drive CPU as well as possibly DMA operations. And then we have 2 peripheral clocks. One is SM clock and the other one is high-speed SM clock. And these two are mainly used to drive different peripherals such as ADC, high-speed timers, as well as communication modules. There are 2 additional clock taps that we can use on MSP432. These are the low-frequency clock taps, A clock and B clock. So these 2 particular clocks are particularly useful in low frequency and low power modes since they are optimized for ultra low power consumption. So in particular, A clock and B clock can operate anywhere from 128 kHz all the way down to 10 kHz. So as you can see, we have a pretty flexible array of clock sources as well as clocks that we can use on MSP432. The checkboxes here that you can see are the possible configuration. So for example, you can use DCO to drive M clock, or you can use MODOS to drive SM clock, and so on and so forth. One particular clock source that we would like to cover in more details that is unique to MSP432 is the DCO. On a typical DCO system, the user can select from a number of pre-calibrated frequencies, and these pre-calibrated frequencies are usually pretty accurate, even across temperature and voltage. However, if you need to come up with your own frequency that is not one of the pre-calibrated values, it is also quite difficult to do so on a DCO system, which typically requires calibration that needs to be done at production. So the DCO of the MSP432 introduces a new way of doing on-the-fly calibration. So first off, the DCO still provides 6 pre-calibrated frequencies, starting at 1.5, 3, 6, all the way to 48 MHz. But what's new about this DCO system is that it allows you to tune to any particular frequency in between these ranges. So starting off with the pre-calibrated frequency, for example, at 12 MHz. Now the range for this DCO range will be starting from 8 all the way to 16 MHz, and using a DCO tune register and a mechanism to tune, you can actually tune to any frequency value between 8 MHz and 16 MHz to the accuracy of 2 to the power of 12 steps. So this unique capability allows you to, on the fly, retune your DCO to any frequency that your application needs. if you have a particular communication baud rate or UART, for example, that is not met by any of the existing calibrated frequency, you can use this on-the-fly tuning capability to determine your exact frequency that you need. Not only providing you with a tuning capability, the DCO on MSP432 also maintains high accuracy across temperature and voltage. Using the internal resistor, you can achieve around 2.65% accuracy. However, you do have the option to improve this accuracy all the way down to 0.04% using one external resistor of value 91 kilo ohms with 0.1 tolerance. With the help of MSP432 driverless API, you can actually just use one API to tune your application to any frequency between 1.5 all the way to 48 megahertz. Moving on to memory. On the first device of the MSP432P series, the MSP432P401R, the flash memory comes with 256 kilobytes worth of memory. The flash operates at 16 MHz and it also contains speed boost capabilities with 128-bit buffer and prefetch mechanism. The MSP432P401R also comes with 64 kilobytes of SRAM memory. These 64 kilobytes are broken down to 8 banks, each with 8 kilobytes of memory. This allows you to individually control the power to each SRAM bank to optimize the power. The MSP432 also comes with 32 kilobytes worth of ROM memory. What's stored into ROM is a robust MSP432 driverless APIs that are integrated to save the application space. ROM memory also requires less power to execute ROM. In addition, it also requires a single cycle execution all the way up to 48 megahertz. So that is definitely a plus and a benefit when using ROM. The MSP432 also comes preloaded with a bootstrap loader or BSL. This BSL is pre-programmed into the flash memory. However, you do have the option of reprogramming with your own custom BSL. However, the factory BSL comes preloaded with all 3 serial communication flavors provided, including UART, I2C, and SPI. So you can use this serial communication mechanism to upload your firmware in the field in the event that JTAG access is no longer possible. So starting off with flash, the flash architecture on MSP432 is that the flash is broken up into 2 banks, each with 128 kilobytes. The flash memory is also organized into sectors, with each sector size being 4 kilobytes. This allows you to individually control, protect, or unprotect each sector from any erase or write operation. So this can become quite handy when you need to perform a mass erase on the whole memory, and you can still individually protect certain flash sectors. Since the flash memory is organized into 2 independent banks, the developers can actually leverage this feature to simultaneously read or execute from one bank while perform an erase or possibly even program operation on another. This allows the application to not waste any time on flash operation and can actually execute code in parallel. As we mentioned before, the flash memory executes at a maximum speed of 16 megahertz. So when the system is running at higher speed than that, all the way up to 48 megahertz, a buffer is required in order to improve the effective speed of the flash. So we have implemented a 128-bit buffer that allows the CPU to prefetch memory into the system while running at a higher speed than 16 megahertz. For various flash program and erase operations, the flash controller also provides a hardware engine that assists with certain operations, such as to make the verification process a little bit easier, or to perform a burst mode when it comes to writing to flash. In addition to the flash controller, the MSP432 also enables several flexible code security and protection options. We will cover this in the later sections. To quickly cover the highlights, you can use the ARM-provided memory protection unit to individually secure and protect each flash memory region from execution, from writing, or from reading accesses. Software IP vendors can also leverage up to 4 IP-protected memory areas to securely deliver the black box IP solutions to another customer. Again, this feature will be discussed in more details in a later section of the training. On MSP432, there are 64 kilobytes of SRAM memory, and this 64 kilobyte of RAM is broken up into 8 dynamically configurable banks, each with 8 kilobytes of memory. For each of the SRAM banks, there are 2 options that you can choose in order to optimize for power consumption. First off, you can actually enable or disable the banks entirely, and this will shut off any power consumption to the bank. The second option you can also choose to retain or not retain the content in LPM3 to minimize the SRAM leakage power consumption. In this scenario, all 8 SRAM banks can be active in active mode. However, for the SRAM banks that do not to retain the memory, you can choose to dynamically disregard this content and shut down these banks when the device enters LPM3 mode. This allows for less SRAM leakage power consumption of the device, ultimately driving the overall device power consumption significantly down. So the MSP432 follows the standardized Cortex-M memory map, starting off with the flash memory located in the first area in the memory, starting at 0x00. This is where your interrupt vector table as well as your main application code reside. Moving on, the ROM memory is located at 0x01 million. This is where the MSP432 peripheral driver library or driver lib is located. Next, you have the SRAM region, which is also bit banded into the bitband region of SRAM. Next, you have the SRAM memory located at 20 million. The SRAM memory region is also being bit banded, allowing you for individual bit access. Moving on, you have the peripheral registers being located at 40 million. The peripheral memory is also being bit banded, allowing you to individually control each bit of each peripheral registers. Last but not least, you have the instrumentation as well as the debugging interfaces. These registers are located at the very end of the memory map, starting at 0xe0 million. So tying everything together, in this section we have covered the clock and the memory system, and in the previous section we covered the power management system of the MSP432. And there are actually quite a few dependencies between these modules. Having a better understanding of how these modules are related to each other will definitely help you build a more robust and more efficient MSP432 application. So first off, the number one requirement for any application is the CPU speed. And depending on the CPU speed, you must determine the right power management configuration as well as the memory configuration that meets that requirement. So for example, on MSP432, if the system runs anywhere from 0 to 24 megahertz, you can use the vCore level 0. However, if the system runs anywhere from 24 to 48, you will need to boost the vCore to level 1. As mentioned earlier, the flash also operates at up to 16 megahertz. So if the system runs between 0 and 16, you don't need a flash wait state. But anywhere from 16 to 32, you will need to increase the flash wait state to 1. And similarly, if the system runs from anywhere between 32 to 48 megahertz, you need to increase the flash wait state to 2. Last but not least, one thing that could contribute significantly to overall device power consumption is which regulator to use at which frequency. If you could recall from section 3, when we talk about a power management system, there are two regulators provided on MSP432, the DC-DC as well as the LDO. And usually, the DC-DC use higher efficiency than the LDO at higher speed. So as you increase the system frequency, you might want to start thinking about investing in using the DC-DC. So with that, we have concluded the part 4 of the training series, where we have covered the clock and the memory system and their features on MSP432. Thanks for watching.